water as an ideal gas. Even the water inside the saturation region still use the ideal gas equations. That's the biggest problem. That's why the average is so low. Okay, and are you alright? No accident. So can we remember that? Don't assume water and the refrigerants as ideal gas.
Can we assume steam is an ideal gas?
Steam, theoretically you can. Actually you can, but we haven't learned yet. You know, as I have taught in week 2, we remember compressibility. Okay, that's a number to identify quantitatively whether we can assume the vapor as ideal gas or not. So compressibility has to be close to 1. Okay, and at very low pressure, the vapor can be assumed as ideal gas. But in the exam, in your future work, okay, you will learn this, okay, and then vapor at the low pressure can be assumed as the ideal gas, just like the water, you know, vapor in the air, okay, we breathe. The pressure is very low, like 20 kilopascal, 17 kilopascal partial pressure. So it can be assumed as ideal gas. But in this subject, you know, to make sure you wouldn't be confused by ideal gas and water and refrigerants, don't assume water and refrigerants as ideal gas. Okay? Because you know, in the questions, the properties you can find from the property tables. Okay? For water, for refrigerants, you can find from the property tables. So what's the basic methods to determine the property? For example, the question asked to find out the temperature or enthalpy or whatever. For water and the refrigerants, what's the basic methods? I asked this question yesterday. Yeah, some of you may not be here. Can we remember?
Two independent properties.
Tables, yeah. How to use the tables? That's right. Yeah, use the property tables. Appendix B, right? 2 independent properties. Okay, otherwise, which table are you going to use? Okay, and with only single property, you may find 100 degrees Celsius in all the tables. Okay, which one? By knowing 2 independent properties. If you forgot this, please write them. Okay, for water and the refrigerants, by knowing 2 independent properties, we can find others. We have used these methods since week 1, right? Yeah, if we still say we can't remember, I think then our memory would be shorter than fish's. Anyway, okay, I just make a line here that's for. And then ideal gases, you know, we have PV equals RT, we have the H equals Cp dt. U equals Cv dt. And also we have the formula for calculating the specific enthalpy change. Okay, I just going to open space later when you see that. Okay, and also in the study guide, the second page, there is a flow chart to show you how we learn in order. Okay, and here I just highlights multi-phase fuel substances. Actually, we have only dealt with water and refrigerants. Okay, and then ideal gases. And what are the 6 properties? Okay, if we still don't know what the 6 properties are, I think we'll be in trouble. Okay? So I just listed in week 1, the ideal gas law, okay? And then all these concepts, do we understand? Do they look very strange to us? What's saturation pressure? What's saturation temperature? What's quality? Why do we need quality when the state is inside saturation region? Because saturation pressure, saturation temperature, they are dependent. Okay? If we know only pressure and temperature inside saturation region, that's not enough for us to determine the other properties. That's why we need a special property which is called quality, which is defined by the mass ratio of the vapor. Okay, mass ratio, not volume ratio. Okay. Just follow this, and then for everything related to processes, we have dealt with 2 different systems. If we just define them in terms of mass transfer across the boundary, okay? One is called closed system, the other one is open system. The major difference between these 2 systems is the mass transfer across the boundary. So for closed systems, mass is constant. There is no mass transfer across the boundary, but depends on where you define the system boundary. Okay? We will see some examples. Okay? And the application of the first law and the second law to closed systems, what kind of closed systems we have had, and what kind of the steady state, steady flow process, transient process, we have learned, okay, for open systems. Both first law and second law. And you will see the questions from the previous examples. You can see, the questions won't be only for first law, won't be only for second law. Okay, they will be together. Okay, and as we know, probably I just follow this one. Okay, that's the second law, and then we look at the second. Okay, for example, I've given some particular example, okay, constant volume process, no moving boundary for closed system, okay. When you look at these equations, we must understand the conditions. What are the conditions? Kinetic energy change is 0, potential energy change is 0, okay. So that's why the first law energy equation becomes like that, okay? And from here to here, if it's a transient process, we can't do that because mass is changed during the process. And in a closed system, mass is fixed. So we have total internal energy is equal to constant mass times the change of a specific internal energy. Okay? So what's the general equation, and how it's simplified like that? Okay? That's very important to understand the conditions. Constant pressure process, that's our first quiz, right? Okay, I think we've done a lot of examples. Piston cylinder arrangement, that's the physical model, okay? And it's quasi-equilibrium constant pressure process because the energy transfer, that's why the piston is looped. But in the macro scale, we assume the process is constant pressure process because the outside pressure is unchanged and the process is slow enough for us to assume it's a quasi-equilibrium process. Okay? If your quiz 1, you didn't do well, you had something you still don't understand, you must go back. Okay? Constant pressure process. Okay? In the closed system, how to apply the first law, how to apply the second law. Okay? Closed system, if the system defined like that, we know the process is started, in this example, it started by opening this valve. During the process, part A and part B, they have different properties. So it's called non-uniform closed system. Okay, you can define two systems, but you will have two open systems. Okay, because there is a mass transfer between these two, and I explained why we need to define like that. Okay, to simplify the solution. Okay, and if the boundary is defined like that, then there is no moving boundary. Okay, no moving boundary. That's why the energy equation is the same as the one for constant volume closed system. Okay, when we ignore the kinetic energy change and potential energy change. However, the detailed calculation of the internal energy, total internal energy of the initial state and the final state are different. Okay, because the mass transfer happened between these two paths internally. Okay, so that's why you need to find out the mass in each of the paths in order to find the internal energy at state 1 and state 2. The other concepts like properties, they are only functions of the initial and final states. Doesn't matter what's happened during the process. Okay, the property change only calculated for the initial property and final property. Okay. But heat transfer is the function of the path. Why? Because the heat transfer is equal to, property change plus work transfer. Work transfer is a function of path. Okay? So all these concepts you need to revise. And that's another example. Non-uniform system with moving boundary. But here, the most complicated case is a constant pressure process in part B. Okay, nothing more complicated than this one. And then the volume change. We know in a constant pressure process, work transfer is equal to the pressure times the volume change. Okay, in this case, volume change is only the volume change in part B. Okay, in part B. Okay, so here, just to give the equation, then you can see now work transfer is not 0. Okay. But work transfer is easy to calculate as long as we know the volume change in part B. And part A, volume is unchanged. But normally we look at the total volume, okay, including part A and part B. As for closed system, and here I have some more examples not in the listed in the study guide. And for example, if the pressure, the function between the pressure and the volume is controlled by a spring, and then the function between the pressure and the volume will be a linear function, and then the work transfer is equal to the area, is proportional to the area under this straight line, and bounded by V equals V1, V equals V2. And this is not only for this example. All the work transfer, integration of the PDV, okay, the results is like that. So on the PV diagram must be on the PV diagram. Okay, the proportion actually is the mass. Okay, so this area, the value of this area multiplied by mass. This example just means as long as we know how to calculate this area, you may not need to do the integration for integration in PVB. Okay, you just that's something you learned from high school, how to the average height multiplied by the base. Okay, so that's the area. And also another non-uniform system, with internally with moving piston. But in this case, actually, if we define the boundary with the red line, there is no moving boundary. Even piston is moved because of the pressure differential between part A and part B, but that's not cross the boundary. Okay, so all these concepts are important. That's why rather than memorizing the solutions of particular examples, we better just master the concepts. Doing the examples is to enhance our understanding of these concepts. This subject you can feel is very different. Even this subject and the fluid mechanics and heat transfer, these are the three subjects in one stream, thermofluids, but you can see they're very different. I think they're probably the easiest one is heat transfer. I would love to teach you heat transfer, but I never got the opportunity yet. So probably that's not unfair. If Java heard about this, he would be upset. But the heat transfer basically is three types of heat transfer, and from these empirical equations, not so much like thermodynamics. And fluid mechanics, the double integration, triple integration, and a little bit concept, similar to the first law, but you need to define control volume, whatever, but nothing like entropy. Okay, nothing like entropy. The concept sometimes can be abstract. But if you have learned something difficult to learn, so your achievement is significant, and we should feel excited. And if you are going to work work in like a power station, definitely you will, apply your knowledge about Rankine cycle, and the gas turbine, internal combustion engines. Even you are not working on engines, but everyone got a car. At least we know something not everyone knows, right? Anyway, okay, and then so for the examples we have had here, okay, closed system. Application of the first law, most cases we have ignored kinetic energy change and potential energy change for closed systems, okay? And then definition of work transfer, and also with work transfer for different processes. Additional to constant volume process, constant pressure process, and the linear function between the pressure and volume, we have learned polytropic process, okay? Polytropic process is a typical process in an engine, compression stroke in an internal combustion engine, compression stroke and expansion stroke. And also for the polytropic process, we understand you don't have to if you have a question, I didn't mean you must have a question like that. You don't have to derive the formula like that, okay? But we need to understand, the index equal to 1 and not equal to 1. We have two different integration results. Yes?
Did you say that you use internal energy when you have a constant volume process?
No, polytropic process. Compression process is a polytropic process. Expansion process is polytropic, another polytropic process. Constant volume is the combustion process in Otto cycle. Yeah, we'll quickly go through that, even we only had that last week. Is that your question? Yeah, okay. Okay, and the application of the second law. Okay, closed systems. Actually, that's the general equation for any total entropy change. But this one is not in the rate form. We know for steady state, steady flow process, this calculation is in the rate form. But just remember, total entropy change or net entropy change or entropy generation. Okay, three names for the same thing. Total entropy change, net entropy change, total entropy generation is equal to the system entropy change plus the surrounding entropy change. But we need to understand for different systems how to calculate the system entropy change, how to calculate the surrounding entropy change. Okay, that's the key thing. Knowing this first, but detailed calculation of the system entropy change, detailed calculation of the surrounding entropy change. We need to understand this. For a closed system, it's simple. System entropy change, just system, specific entropy change multiplied by mass. Okay? And then how to find this depends on the working freeze, whether it can be assumed as an ideal gas or not. Okay? Whether you are going to even ideal gas, whether you are going to assume Cp, Cv constant or not. Okay? And the surrounding entropy change for